Hi everyone! We've done some examples working with a formula and a graph, and I just wanted to tack on one more where we work from a table just so that you've seen several representations. So we have a table that tells us the temperature of a potato in degrees Fahrenheit at various points in time. The time is measured in minutes. So this potato goes in the oven, we track time in minutes, we track temperature in degrees Fahrenheit, and the data's been recorded here. And our first job is just to find the average rate of change of the temperature from t equals 15 to 45. So this isn't anything terribly new. 15 to 45. So those will be our 2 points, which means we need 296 minus 180.5. divided by 45 minus 15, which gives me 115.5 divided by 30. And I crunched this and got approximately 3.85. And that's actually not even approximate. That was exactly right. I didn't have to round to do that. We want to make sure we include units in our answers. So if we think back to this, the 296 and the 180.5, those are temperatures in degrees Fahrenheit. So this is change in temp, which will be degrees Fahrenheit. And in the bottom, we had the time. So this is change in time, which is in minutes. So this should be degrees Fahrenheit per minute. So now that we have this average rate of change or slope of a secant line, we can use it to make predictions about what's happening at points that are not on our table. So we're asked to estimate the temperature of the potato when t equals 46 minutes and then again at 50 minutes. And we're supposed to think about that a little bit and analyze it. So for t equals 46, I'd go back over to our table and say we have one piece of information that's very close to that. At 45 minutes, the temperature was 296 degrees. And what we've just discovered is that on average, between the 15-minute and 45-minute mark, the temperature was increasing by 3.85 degrees Fahrenheit per minute. So if we want to estimate f of 46, we would say, well, that should be in the ballpark of that 296 degrees at 45 minutes, plus the 3.85 additional degrees for the one additional minute that has passed, which should give us 299.85 degrees Fahrenheit. And I would expect we've only gone a minute outside of our time interval that we calculated the average on. This is probably a pretty decent estimate. We're then asked to check out f of 50, and we can use that same thinking. I would still say 45 is our closest point, so I'm going to keep using it. Technically, you could use any point. I would expect to get better estimates by using closer points because we have no idea what kind of curve shape this might have. So I will stick with the 296 as a starting point. That was after 45 minutes. And then our best estimate was that it would increase by about 3.85 degrees per minute. And we've now gone from 45 to 50, so that's 5 minutes. And from this one, I got 315.25 degrees Fahrenheit. And basically what we're doing here is we're building a linear function. So we're saying, okay, f of t can be approximated by 296 plus 3.85. And then we just have to be a little bit careful here. What we're plugging in is not the t. We're plugging in the t minus the 45 minutes. So in the parentheses, we're really seeing how far from 45 minutes have we gone. And this is basically finding the equation for a secant line and using it to make predictions. We don't expect them to be perfect, but we do expect them to be fairly reasonable estimates of what is happening. So in a situation where we have a fairly complicated function or where we have incomplete data and we'd like to estimate what's happening in between, this is a great strategy.